we have this finish the proof of this theorem that gave us a depth 4 reduction. So any degree d polynomial with size S circuit with no restrictions, right? This can be the only restriction is that it is a homogeneous circuit. Then with that you can bring it down to depth 4, where the two multiplication fan-ins are, the product fan-ins are very special. So the top multiplication fan-in is d by t, and the bottom multiplication fan-in is only t for any t. With size only s to the t plus d by t. So if you take t to be square root d, then multiplication fan-in square root d could give you depth 4 circuit of size s to the square root d instead of s to the d being, so s to the d is the trivial. Okay. And so we will not discuss that, or maybe we will discuss it after the mid-sem. Some lower bound theorems that will suggest that this reduction is kind of optimal. So in depth 4 you cannot improve. Although s to the square root d looks bad, but you cannot really improve it. Okay, so the circuit size may only be s, but when you squash it down to depth 4, then the price you have to pay will usually be s to the square root d.
Okay. Will it be like we know we can't reduce it, or will the theorem be like if we can reduce it, then something bad will happen?
No, so we will give a no. I think it will be an unconditional result. So I think we will show that for iterated matrix multiplication, for which there is obviously a small arithmetic circuit that can do the multiplication, we will show a lower bound of s to the square root d for homogeneous sigma pi representation. So if you want to do iterated matrix multiplication, say you want to compute the top left entry, you are say multiplying n cross n matrices, d many of them, so the degree of the polynomial you are computing is d. This obviously you can write down a circuit which will be small, but when you squash it down to depth 4, then the depth 4 representation, homogeneous sigma pi with square root d fan-in representation will be this s to the omega square root d. So this big O actually becomes a theta in that case then, for that specific problem of IMM. So I think we'll do that after the mid-sem as a lower bound result. And if you can do something better, so if you can find a polynomial for which this type of a representation requires size n to the little omega square root d. So instead of big omega, if you can make it little omega, then actually you have proven a super polynomial circuit lower bound result. Okay. So such a polynomial cannot be written in a small sized circuit representation. So that is really the key motivation for the depth reduction to this extreme extent. And now we will do something even better. Okay, so the question we ask is, could we reduce this sigma pi sigma t to depth 3 in some non-trivial way? And so the answer to this will be yes, as we will prove. but this will assume high characteristic or zero characteristic. Is there anyone who doesn't understand what is characteristic of a field? Okay, so yes. No. This is what comes into the picture is just 1 over n factorial. If that doesn't exist, then there is a problem. So this is called depth 3 Kazam result, and the previous theorem that we showed, the Agarwal-Vinay result, was originally called depth 4 Kazam. So Kazam means that this is the depth at which point things become suddenly very general. So depth 2, for example, is the kind of the trivial case, and if you go to depth 3, then suddenly you are able to connect with general circuits with unrestricted depths. So this theorem is due to Ankit Gupta, Pritish Kamath, Neeraj Kayal, and Ramprasad Saptarishi. Okay, it's not too old. It says that same thing with sigma by sigma. So let f be a degree d polynomial with a size S circuit. Over f, and let us think of f as the field of complex rationals. It could be any characteristic 0 field. In fact, you will see in the proof that it suffices if the characteristic is more than d. So maybe I also add that. Just more than the degree. Then there is a sigma pi sigma square root d circuit of size S to the square root d, exactly computing f. Okay, which should be a shocking result, right? So you are given a general circuit of size S, and you are able to squash it and bring it down to depth 3, which is just sigma pi sigma. Okay, this is just a representation where you are adding a bunch of products of linear polynomials. So this was not really conjectured before it was shown. Okay, it never looked possible. Even if you are given depth 4 Kazam result, even after that this doesn't look possible, because how do you compress 2 multiplication gates into 1? Right, they are doing very different things. So the proof will be highly counterintuitive, as you will see. So one very counterintuitive thing will be that although f is a degree d polynomial, this multiplication gate in sigma pi sigma will have a huge fan-in. Its fan-in will be S to the square root d. Okay, so these products of linear polynomials, they will be computing a product polynomial which has far more degree than the degree of f, but then all these product gates will come together and things will cancel out and give you f in some non-trivial way. This, by the way, did not happen in depth 4. In depth 4, the multiplication fan-ins were even smaller than d, right? And together they were giving you only things around degree d. They were not really computing something much bigger than degree d. But here it's different. So something something counterintuitive will happen in the proof. Okay, so let us just realize what this model is. So sigma pi sigma m model computes things like sigma sum of products of linear polynomials I1 to k j up to some degree di, and Lij is a linear polynomial in how many variables? So this m is the fan-in of sigma, right? So in m variables, m may be much smaller than n, which will be kind of the case we are in. Sigma fan-in will have actually only square root d, the bottom sigma fan-in. So it might be actually adding just few variables, taking a linear combination, and k is the top fan. Okay, so that is one thing about the model. The second thing is that this model is inherently inhomogeneous. We get inhomogeneity. That has to be the case. Where both top fan-in k and the di's could be very high, s to the square root d. Okay, so it's inhomogeneous, and these other things which are unspecified, k and di's, these can be as high as the size. This inhomogeneity has to be there because well, your product gate is multiplying a lot more things than you needed, right? So if this model was homogeneous, then you will never be able to get back f. So it's actually the inhomogeneity is the beauty that can cancel things out. So it produces not only high degree monomials but also all these lower degree monomials, and then the higher ones cancel and the lower ones remain to give you the sum as f. So is the theorem clear? Okay. So let us go to one interesting consequence which you can see as a new classical result. Something telling you about determinant, okay, which was never known and not even believed. So determinant has a non-trivial depth-free representation. So by definition, determinant is defined as a sum of product of variables, right? But then these products are how many? For n by n matrix, it's n factorial many. So n to the n many. So that n to the n can be reduced to n to the square root n. Okay, so there is a efficient, well, not really efficient, but a non-trivial depth-free representation. So over Q or over complex, whatever, n by n determinant has a n to the square root n size sigma pi sigma square root n circuit. Okay, so remember that determinant is defined in this sigma pi form, and then its size is n to the n. But if you look at it sigma pi sigma with sigma, this bottom sigma fan in square root n representation, then it can be done compressed much more, all the way to n to the square root n. Okay. So from the definition of determinant, could you ever deduce this? Right, it is, you cannot even conjecture this. How do you show this now? Using the previous theorem?
It's just given that it's d is root n and
Right, so you have to observe that determinant n by n has n square variables, but degree is only n. And you have seen in multiple ways you have seen circuits of size poly n for determinant. Right, so you get s to the square root d, which is n to the square root n. Right, so that's this actually is shedding light on something very basic. Right, you learn something new about determinant, and that you have been doing every other week. Right, you learn new things about determinant. So what we don't know is these two conjectures. So first is that determinant n, we conjecture that it cannot be done any better. So determinant requires n to the omega root n size sigma pi sigma root n circuit. So this sigma pi sigma representation is optimal, that is in fact any depth 3 representation. So depth 3 representation for determinant, this thing is optimal. This is the optimal, this is the only way in a sense to express determinant in depth 3. And so second conjecture is that, so this is a question, and second is that permanent requires so what do you want to say about permanent in depth 3 representation? So what do you know about depth 3 representation of permanent? N to the n is by definition, but there is something better you have seen, right? This Reiser's formula gave you 2 raised to n. But in that 2 raised to n, if you recall the formula, the bottom fan-in was not square root n. In the bottom, actually, it was an inner product of all the variables with a fully supported vector. So bottom fan-in was actually n. Intuitively, it seems that if you want to reduce that to square root n bottom fan-in, then what should be the size? Just the definition of permanent, which is n to the n. So n to the omega n. Right. So at the level of depth 3 already, these are reasonable conjectures, and they suggest that permanent and determinant are very different. There should be a gap of this, in the exponent there should be a gap of square root, or in the exponent there is some squaring happening, right. So remember that these conjectures are on omega, big omega. These are lower bound conjectures. So these are, both are big open questions. If you prove both these conjectures, what do you get? Yeah, so this will imply that Vp is different from Vnp. Why is that? You don't even need to show 1, you just show 2. So if you show that permanent requires n to the little omega square root n, if you just show this, yeah, so maybe I write that down. So if you just show that permanent requires n to the little omega root n size sigma pi sigma root n circuit, right, then there cannot be a poly n sized circuit for permanent, because if there was, then the from the previous theorem you would have also obtained n to the big O of square root n, depth 3 representation of this special type, in fact. Right, so just 2 here actually implies something, the basic conjecture we started with, Valiant's hypothesis. But we are conjecturing more than that. So here actually we are conjecturing that permanent and determinant, they are very different. VP VNP is not really the same question. It doesn't talk about permanent versus determinant. It just talks about permanent versus circuits. And we don't know whether determinant is complete for circuits. Circuits, for all we know, may be slightly more general than the determinant model. So determinant is equivalent to what? Yeah, determinant is complete for ABP, so which we defined the class VBP. But VBP, for all we know, could be strictly smaller than VP. Okay, so so this is what we have now, and this gets connected. So Valiant's hypothesis is now connected to optimality of Reiser's formula. Right, and who knew? This was not clear before, that VP VNP question is just about the whether this Reiser's formula is optimal. Right, it gives you 2 raised to n, and if you can show that that is optimal, you cannot improve that depth 3 representation. Then again, by this sequence of connection, you will prove VP different from VNP. Any questions? So then we will dive into the proof, and there will be a lot to dive in. So the proof requires a host of ideas. And initially you will not understand why we are doing what we are doing in the proof. Okay, so it will be, for a while it will be magical. So just to guide you through that process, so one common feature is change of basis to express polynomials. Okay, so one common feature is to use powers basis, let's say. Or basis of powers of polynomials instead of the standard basis, which is the basis of monomials. To express polynomials. Over this, for now, characteristic 0 field F. Right, so this idea is very suspect, right? To go from depth 4 to depth 3, why are we looking at powers, sum of powers, right? That already, I really have no answer for that. So let's just continue. So the outline is that from a general circuit, we will go to depth 4 representation, which is sigma pi circuit. This you have already seen. Then from here we will go to something you can call it depth 5. So sigma wedge, sigma wedge, sigma. What is wedge?
About
Yeah, so wedge is like a product gate, but all the inputs are the same. Okay, so since the inputs are the same, your multiplication is just actually giving you a power of this one single input of the first input. So it's a special multiplication gate, and then this is depth 5 now. So we'll actually increase the depth. We'll go the opposite way instead of reducing the depth. And from there we'll suddenly jump for some reason to sigma pi sigma. Okay, so from 4 we go to 5, and from 5 we go to 3. This we will do. So okay, let us specialize this to the field is, suppose, the field of complex. No, the field is the field of rationals. I was given a rational polynomial. So this sigma pi sigma will actually be complex, will have complex coefficients. But that is also, so you are going to constants above your field. So then you have to, in one step, you will have to come down to rationals. Sigma pi sigma circuit over rationals. Okay, so this will be the end. So we will convert our polynomial f from general circuit to sigma pi sigma circuit over Q, and we have to keep analyzing the size. So this is already done. This is step 0. This is step 1, step 2, and step 3. Okay, so these will be the 3 new steps that we have to describe. Is the outline clear?
is it because of the depth 5 circuit we are keeping the characteristics of the field 0?
So step 1 requires characteristic 0. Only step 1. Other steps are characteristic independent. Step 0 definitely was, and step 2 and step 3 will also be characteristic independent. Well, step 3 you have to define what does it even mean. So step 3 is actually the weakest step. It is not of great interest. Step 1 and step 2 are the most interesting ones, but step 1 is the reason why we need characteristic 0 or bigger than the degree d. Step 2 is also very interesting, but fortunately it works for any field. Doesn't matter, I mean for any characteristic, as long as the field is big, which we can always assume. Okay, right, so just to recall, step 0 is done. So what do you mean by done? So let F have a circuit of size 0, S0. Let F have a size 0 circuit, let's call it C0, n variables. So by this depth 4 chasm or depth 4 reduction, we get a size S1 equal to S0 to the square root d. Homogeneous sigma pi sigma pi circuit, let's call it C1. Okay, so C0 you start with, C1 is your depth 4 with these special product fan-ins, both square root d, and the size is S0 to the square root d. degree of f is d. Okay, so now we want to convert this into sigma wedge sigma. So basically we want to replace these general multiplication gates by very special ones. So that will be step 1. How do you change the product gates? So we show a general way to change basis. That converts pi to sigma wedge. So change of basis will basically be this changing product gate to wedge, but then this, as you can immediately realize, is impossible, but it somehow will become possible if you take a sum of powers. Okay, so we are basically writing a product as a sum of powers.
So is this the symmetric polynomial kind of a thing where you can?
Yeah, so this product is your elementary symmetric function, and this you are no. So there, we were only interested in expressing it as a function of sum of powers. But here, it's even stronger. We want it to be a sum of powers, not a function. There should be no extra function. This will just be a syntactic translation. This doesn't need any assumptions on what the product is. So this is actually given by Fisher's lemma or Fisher's trick. It's a simple statement. If characteristic of the field is bigger than R or 0, any expression G where you have sum of products of polynomials, in the product you are multiplying R things. Okay, so you have this kind of depth 4 representation where in every product gate there are only R inputs, characteristic is bigger than R. This you can rewrite as can be rewritten as a sum of powers. Okay, so we are replacing this each of these products by a sum of powers, and then we are taking the sum. So ultimately G can be expressed as a sum of powers. So what is K prime? What do you think? It is at least K, but how much will it blow up? Right, so we'll show that it blows up by 2 raised to R. Exactly. Every product we will express as a sum of 2 raised to R many Rth powers, and degree of Gi doesn't blow up. Okay, that bound remains the same. Essentially, we will just take linear combinations of Gij's. So whatever was their degree bound remains the same remains for Gi. Yes.
Like taking like subsets and stuff and
Mm-hmm.
doing things with that.
Yeah. So this proof you have seen in Reiser's formula. Yeah. Correct. So the proof you have already seen actually. So recall Reiser's formula proof, which was basically this Y is permanent in VNP, that proof. So permanent R is in VNP. So that there you have seen the ideas. So this y1 dot dot yr, this monomial, right? This is essentially permanent of a matrix. What is the matrix? Yeah, the same rows. So these equal rows, permanent of this is just r factorial times the product of these row entries, and that in that proof you were able to express this permanent as a sum of product of linear polynomials, where these linear polynomials are just inner products. So I can just directly write it as this. For all subsets. So, well, the only new thing is this part. Now this is a perfect power, and why is that happening? It's an rth power because in that old formula, these linear polynomials you got in the product gate, they were the same inner product. So now since all the rows are the same, you get same factors. So in other words, you get rth power. Okay, so y1 dot dot yr, this product can be written as a sum of powers with very simple coefficients, but the problem is this r factorial. So r factorial inverse should exist. Otherwise, even if it vanishes, then you don't get anything about y1 dot dot yr. So this should not vanish, that's all. So as long as it doesn't vanish, we have a representation for the product, for a general multiplication gate. So, and then we can apply this on each product.
So are we converting the product gate to the sum of powers of sums, right?
Sum of powers of linear polynomials.
Yeah, so that should be like sigma wedge sigma, right?
Oh, in the idea you are saying? Yeah, sure. That is true, yes. Yeah, I did not mean sum of monomial powers. That would be impossible again. So apply this on the ith product gate, which is computing gi1 dot dot gir. So you will replace these yj's by gij's. It is just a simple combination of gij's. So degree is obviously bounded, and what is k prime? So how many summons, how many powers are there? The number of subsets, right? So that is 2 raised to r. To get a sum of 2 raised to r powers. rth powers, which implies the lemma statement. Okay, so the fan-in, the cost is that fan-in increases exponentially in R, but it is a simple exponential function. Can you do this thing over other characteristic? So will this Fisher's trick exist for other characteristic?
If you go below our R factorial, the characteristic would divide R factorial.
Yeah, but that is in my proof.
Yeah.
Do you have a proof where it doesn't? So that is in the assignment. Solve the assignment. There is a question that it's impossible. So this business is actually, I mean, this pi to sigma wedge sigma representation, this basis change requires characteristic to be large. Otherwise, it doesn't exist. It is provably impossible. Okay. So once we have this, we will use it on sigma pi representation. So on product gates, with fan-in square root d, on circuit C1, we get, so yeah, this has to be thought about carefully. So you have these two layers, right? On the bottom pi, you will apply this transformation.
So take the polynomial for characteristic P, take the monomial x1, x2 times xp
x1, x2,
times xp.
there are only three variables.
And x1, x2,
Dot, dot.
xp, xp.
Yeah, so let's say characteristic is 2 and you are looking at x1, x2.
Yeah, yeah.
Mm-hmm.
So now if I can express it as Ci, Gi to the P,
Sure, yeah.
that would mean that by binomial I can, that means x1, x2, xp is like powered P, which is not true using multinomial.
Yeah, so you have to solve it in the assignment. We cannot discuss all the details here. There are some details. I mean, you have to also remember that this R is merely an upper bound, right? This, when you are multiplying R things, many of these things may just be 1. So when you are looking at x1, x2, it doesn't mean that you have to express it as a sum of squares. Maybe you can express it as a sum of cubes or sum of 4th powers or sum of 100 powers.
Also, in the G equal to Ci, Gi to the R, that is like R prime where R prime.
No, not R prime. It is,
Exactly R.
it's an upper bound on the multiplicative product fan-in. But many of these things, all of these things may be 1. It's merely an upper bound. So when we say that the basis change is impossible, then you have to show that no powers, whatever be the exponent, can produce your polynomial. Yeah, but don't get distracted here. You can do it at home. So what you have to think here is what happens when you replace this pi by Fisher's trick. So this is not a single pi, obviously it is in the layer, bottom layer, so there are many multiplication gates. Each of them you will replace by sigma wedge sigma, and that already has increased the depth by 1, right? This is now depth 5. And what happens to the top layer of multiplication gates? So when you replace them by sigma wedge sigma, since it is already sandwiched between sigmas, this will not increase the depth. Okay, so you get depth 5. So this gives you a sigma wedge sigma circuit. C2 of size S2, which we have to calculate, but first let us look at the fan-ins here. So what is the fan-in of the bottom wedge? Is what? Right, so since it was pi root d, so if this is pi r, then pi r is going to wedge r. And not only that, this bottom sigma is also just r, right? So this is the change of basis we have deduced from Fisher's trick. So using that you get these are square root d, both of them. And what else do you know? The top wedge, that is also big O of root d. Yeah. Others are general, so they can be very large. So these three fan-ins you have guaranteed to be small. And what happens to the size? So C1 was of size S1, let us say. So how on top of that, how much multiplicative growth are you doing? So each transformation will cost you by 2 raised to square root d, right? So this is 2 raised to big O of square root d. That's it. You do it S1 times, which is S1 was S0 to the root d, so that doesn't change. Right, that is fine. Is that clear? So we actually, without paying any price, you have gone from this depth 4 chasm to a very special depth 5, which is sigma wedge, sigma wedge, sigma. Well, but what have we gained? This is no gain, right? This is just increasing the depth. So now what do you want to do? So that will be our step 2. So step 2, now we want to do the opposite, which is convert wedge to product gate. So we show an efficient transformation from wedge sigma to sigma pi sigma over complex field. Wait, what did I define step 2 as? Step 2 here is yeah, so what I am saying is this wedge sigma, I will convert this into sigma pi sigma, and the other one also I will convert to sigma pi sigma. Right? And how will that help?
You just
You club them, right?
No, you just
Club
go
into sigma pi
sigma by sigma by sigma.
Right.
Getting depth 4.
Step 5.
You get back to depth 4, right? That you don't want to do. So why are we doing all this?
Yes.
Yeah, so you will see, while we do this conversion, you will see that you will actually, in the end, when you do these things simultaneously, you will get to depth 3 and not back to depth 4. Okay? You will see why from the trick. So so this thing, well, so I christened it duality trick in 2008. So I'll show that. Okay, so let me state that. So the duality trick is the following theorem. So there exists degree B polynomial so yeah, maybe I should mention why I call it duality trick. So it is duality because in some sense this product addition gate, this is being swapped. Okay, so powering is being written as sum of products. Okay, so it's so in some sense, I mean obviously it is a transformation, but in some sense it is also a dual. Okay, so quantitatively what happens is any degree B polynomial any sum of variables, let's say S variables raised to B. Okay, so bth power of a linear form can be expressed as a sum of product of univariate polynomials. So let me write that down. So there exists degree B polynomial Fi such that the following identity holds. Okay, so the left hand side is power of a linear form, and the right hand side is basically you are evaluating Fi at these different variables of the linear form, taking the product and then taking a sum. Okay, so sum of product of these univariates will give you the power, and this will be an efficient transformation. So there exist these polynomials Fi's. Now, I mean obviously LHS you can just expand fully, right? That also will give you a sum of monomials, and obviously a monomial is of this type. It is just multiplying univariates, in fact distinct variables. But what is the problem? The problem is that there are too many, right? So that is not an efficient transformation. So that is also a dual, but it's an inefficient dual. This on the other hand is an efficient dual because you are using only SB square many products. So that is the point of this over the trivial representation. It's a non-trivial expansion, you can think of it like that. Yeah, so this transforms sigma wedge sigma circuit to sum of product of univariates. For duality trick, well, motivation is to solve identity testing problem for this sigma wedge sigma model, which is sum of powers of linear forms. So sigma Li to the D model, you want to test whether it is 0. Okay, so that's a natural model, but then there is a, as always, there is an exponential blow up happening in just L1 to the D. So how do you test whether these things sum up to 0 efficiently? So for that I convert L1 to the D to this dual, and then I can do identity testing for this case using linear algebra. That I think we'll see if we get time towards the end of the course. Okay, so I will not give my proof because that is complicated. It uses exponential functions and whatnot. So I'll give a proof that is much clearer by Amir Shpilka. So this is just by consider an auxiliary polynomial and then do interpolation. So the auxiliary polynomial he considers is so remember that we are working with only this, right? So we have reduced all our model difficulties into just this case. We are only focusing on sum of distinct variables raised to b, and we want to express it in an alternate yet efficient form. So can you guess what this auxiliary polynomial will be using these z1 to zs? Right, so a polynomial whose roots are z1 to zs, right, kind of. So let us consider this. So let us consider this auxiliary polynomial where the roots are essentially zi's or minus of that, and you see a coefficient that computes the sum of zi's, right? So this is equal to t raised to s plus t raised to s minus 1 sigma zi, and then more complicated things, but we will not care about them. So we will bring this t raised to s on the LHS so that sigma zi becomes the leading term. Okay, so consider f minus t raised to s raised to b. So this will be t raised to s minus 1 b times sigma zi to the b plus lower degree in t. Right. So now what do we want to do? We want to extract this. Right. So think of it as given this, you want to extract the highest degree t monomial. So how do you extract coefficients from a polynomial? No, here you cannot quotient because the remaining are lower degree. If you quotient, then this leading will be killed. So better is to use interpolation. So you actually evaluate this LHS, this function in t for various values of t, and then take a suitable linear combination so that all these lower degree t terms get cancelled. These coefficients don't contribute, and the only thing that remains is this leading coefficient sigma zi to the b. So using interpolation, formula, with respect to the formal variable t. So we want to eliminate t basically. There are many variables, but our interpretation is that t's are only variable, everything else is kind of a constant, and I want to extract this particular monomial in t. Okay, I want to eliminate t. So there is an interpolation formula that also I wanted to do, but I think I'll skip it because it's for this crowd it's standard. That you all know what interpolation is. So let me skip the Lagrange interpolation formula and just say that we can extract using it the coefficient of t to the s minus 1 b in f minus t raised to s b as so sigma zi to the b will be the value that you will get, and this you will get by taking linear combination of evaluations of that function at alpha I and linear combination with beta I. And how many alpha i's will you have to try? How many evaluations do you have to look at? That is basically degree with respect to t plus 1. So that's s minus 1 b plus 1. So those many coefficients are there, and if you want to focus on, if you want to extract one of them, still you have to evaluate the polynomial at maximum number of points, and then there will be these betas which will be special. They will be function of alpha I, such that when you take the linear combination, everything cancels out and you only get the coefficient that you wanted, which is sigma zi to the b. Okay, so this implies that sigma zi to the b is so you can expand this, right? This is just use binomial expansion. Treat f as a single variable. So this is just you just have a difference of two things raised to b. So you can expand it out, and f then is just a product. So you get a sum of products representation. So ultimately you get something like this. Okay, so these j's are all the same, these exponents are all the same here. In this part the exponents are all the same because this big F is a single thing, and then this is being raised to j. So you actually are getting big F raised to j evaluated at some alpha I. So that is this product, many such products for all these alpha i's, and then linear combination. Gamma depends on alpha I. Is that clear? So this is the Fi that we were talking about. Fi is a very simple, it has a very simple form. So that finishes the proof of duality trick, and it is characteristic independent also. Okay. So now what? Now once we have seen this, now we have to apply this. This was a detour. So let us go back to where we were stuck. So we were stuck here, right? So now this wedge sigma and the bottom wedge sigma, we will use duality trick. Let us say we will use it first on the bottom wedge sigma. So that will give us a sigma wedge sigma representation. So the top wedge is actually acting on a okay, let us write that. So thus a homogeneous wedge sigma wedge circuit Yeah, so maybe I should have said that in the beginning that we will now do it like this. We will focus on this sigma wedge, sigma wedge. So this wedge sigma wedge is on which we will apply the duality trick. That will give me sigma pi sigma, which ultimately will give me sigma pi sigma. So let us see why or how. So this wedge sigma wedge can be converted so you are taking power of a sum of powers, right? So in general this is the format sigma zi to the a I 1 to s and then b. So the bottom fan-in is A and the top fan-in is B. So this is the general format, and this now by the duality trick becomes what? So the duality trick actually gave you a very special form. So in that special form, when you substitute, when you replace Zi by Zi to the A, it still remains rather special. Right, it becomes this, and I am saying that this is sigma pi sigma representation, is it? So it is a sum of product, but inside the product this is not a linear polynomial in Z1, it is a general polynomial in Z1. So why am I calling it sigma? Technically it is depth 4, right? Well, you factor it. So it is a univariate Z1 to the A plus alpha A. So over complex it can always be factored completely. Factors will be linear polynomials. Okay, so it's actually a product of linear polynomials.
That is why you get a complex.
Right. So the summoned actually factors over complex to give sigma pi sigma representation. Yeah, so I think I'll stop now at this point. We just have to give the quantitative statements now. So qualitatively what we have done is we had this sigma wedge, sigma wedge, sigma, and this middle part we will convert it into sigma pi sigma by the duality trick. Okay, so that's the duality trick with factorization. So duality trick works for any field, at least Amish-Pilkas proof, and factorization you can do over the algebraic closure, and so together you will have a sigma pi sigma, but since it is sandwiched between sigmas, it's equal to sigma pi sigma. Right, so that is what you get. So that is the moral reason why depth 4 can be reduced to depth 3 for special fields. Okay, so we look at the parameters and especially the fan-in. What is the bottom fan-in? So because it's actually not just a run-of-the-mill depth 3 representation. It's a very special depth 3 representation. So any general circuit you can actually reduce to a special depth 3 representation. So if you can prove lower bounds against this representation, then you have proven lower bounds against general circuits. That is the moral of the story. So any questions? Okay. So